Okay, today we are going to be talking about linear programming and where it's useful. It's dealing actually with systems of inequalities. But I guess the whole idea with linear programming is you can figure out, they use it with like business models all the time. You can figure out how to maximize your cost or maximize your profit and minimize your cost using different little regions here. So we call this little section here a feasible region. Usually you'll have a bunch of things what we call constraints, which is basically all your different equations right there. And based off of your constraints right there, you have your feasible region. And the whole idea with linear programming is every one of these little vertices right here, if you take like whatever the order pairs are, so like this one over here to the right is 7 comma 3, and you have over here I guess 2 comma 3. What do we have here? 4 comma 6 and 2 comma 6. So if you take all of those order pairs and you plug them into your profit or your cost equation, you can figure out which combination, I guess, will maximize or minimize your costs. And actually, I have a real good example that I'm going to attach. It's kind of a separate video, but I'm just going to link it onto, or no, just add it onto the end of this video here. And then it kind of goes through a real world example of this type of stuff. So, oh yeah, I kind of typed it out right there, but you'll see it in the end of the video here. But let me show you how you're going to do like an example on a quiz or a test without as much context. So it's usually the following constraints with the objective function. So here's that right there. It's p equals x plus 3y. And based off of your constraints right there, you're going to figure out how to maximize. I'm assuming P stands for profit. So maybe these have some type of real world tie-ins for this problem right here. So first of all, we got two equations we need to solve for, so we can graph them, I guess. So we're going to say that less than or equal to 6. We're going to subtract over the x. So that'll be negative x plus 6, and then divide by 2. And that'll be, y is equal to less than or equal to negative 1/2 x, and then plus 3 right there. Okay, and then let's do this next one here in red. So it's x minus y less than or equal to 2. So we need to subtract over x, and plus 2. And then actually we need to flip our inequality sign around because we got to divide by a negative. So that'd be positive x minus 2. Right here. All right. So these are all the equations. That one, and then these two right here. Okay. So let's start out with the blue equation here. So starting at 3, and then going down 1 over 2. I'm not sure how far we need to go, so I'm going to just graph that. It's equal to, so it's going to be a solid line. Okay, this next one in red starts at negative 2, and it's got a slope of 1, so up 1 over 2. So there we go. And then we also have y is greater than 0. So that's going to be through your y-axis at 0, so it's kind of like on the x-axis right here. And then x is greater than 0. So that'll be that. So this feasible region right here, region we're looking for is going to be this right here. Now I guess the only thing we don't know is we need to figure out all of your different vertices, and most of them are easy. At least these 3 are going to be pretty easy here. So this vertice here, let's do it purple there. So we got 0 comma 3. Obviously down here at the origin you got 0 comma 0. You're going to have 2 comma 0. And then this one doesn't look like it crosses at a good spot, unfortunately. So this is going to be super clean. But if we want to find the intersection of those two lines, we can just take this y. I'm going to say it's y equals negative 1/2 x plus 3. instead of like writing it as an inequality, we're going to write it as an equation. And then x minus 2. And since those are both equal to y, I'm going to just set them equal to each other. It's essentially substitution. Okay, we're going to add the 1/2 x to the other side. And this is probably why it's not coming out good. So what is that going to be? 1 in 1/2, or 1.5x. Then I guess we can add 2 to cancel the 2's out. So that's equal to 5 right there. I guess that's going to get us a decimal here. I'm going to go ahead and use my calculator so I don't have to think. 5 divided by 1.5. Okay, is x is equal to 3 and 1/3, or 3.3 repeating. So I'm just going to say 3 and 1/3 right there. So that is why that is not coming out good. So that's the x that goes with it. Now I need to go find the y that goes with that by plugging it back into one of these two equations. So I'm going to actually plug it back into that one. So that would be y equals 3 and 1/3 minus 2. So that'll be 1 and 1/3. So that is where those cross there. Not very clean there. Probably should change the numbers. So I guess I was doing this in purple. So let's say that intersection, 3 and 1/3, comma, 1 and 1/3. Now, based off of all of those vertices here, I can go plug all the vertices in to go figure out the max and the min value for this right here. So we're going to go ahead and do that. We'll start out with the easy ones. Oh, okay, yeah, vertices here. I want us to list them out. 0, 3, 2, 0, and then 3, 1/3, 1 and 1/3. Okay, and then we're going to plug them in. So we're going to start out with the easy one. Let me write the equation again. It was x was 3y, I believe. Yep, okay. So we're going to plug in each one here. So 0 plus 3 times 0 right there is going to get us a p-value of 0. Okay, so obviously that looks like it's going to be the min. Okay, so 0, 3, so 0 for x, 3 for y. So that'll be, I guess, 9. You can do 2, 0. So 2 for x, 3 for y right there. So that'd be 2 plus 0, so that'll be 2. And then here's the fun one. It was 3 and 1/3 plus, and then 3 times 1 and 1/3. Alright, so 3 and 1/3 should come out to 3. Yeah, that should come out to 4 actually. So we're going to do 4 plus 3 and 1/3, which comes out to 7 and 1/3. So based off of all of these right here, if this is like a profit equation, we want to stay away from 0, 0 because that's the minimum value. And then obviously the 9 was the best right there, so that was our max value right there. Okay, and then stay tuned for the real world example coming up. Alright, I got a little tutorial here on linear programming. I didn't find a ton of videos that kind of explained what linear programming is useful for, and like good, real world examples that kind of have, some decent numbers that come out. So I made this one example here. Joe is managing a company's production of guitars. An acoustic guitar takes 2 hours to make. An electric guitar takes 6 hours to make. He has a total of 96 labor hours of work. So based off of that, we can come up with an equation. Some of the equations I give you, some of them I didn't. So if you got 2 hours per acoustic guitar, and we're going to define that as A down here, and then 6 hours per electric guitar, and you had total of 96 hours of work with, that can be an equation right there that can kind of give you all the different combinations of guitars that you can make right there. All right, you got a couple of other things here that we have. Due to the availability of the wiring, this company can only make 10 electric guitars a day, and he can also only make 36 guitars, or I'm sorry, acoustic guitars, due to the availability space or the available space in the shipping truck that is hauling. I'm not sure why that doesn't say is hauling the acoustic guitars. So, if Joe profits 45 per acoustic guitar A and 120 per electric guitar E, the total profit P can be modeled with this situation here. So use a feasible region to help Joe maximize his profit. So this is what businesses are all about. They're always trying to figure out how to make the most amount of money here based off of our constraints and what's going on here. So the big first thing here is we're going to go back to this equation. Our hours here, we actually need to be less than or equal to 96. So I actually have that written down here below. So our hours need to be less than or equal to 96, written right there. So, and actually I've already graphed some of these here to speed up the video a little bit there. So that is this diagonal line right here. It's actually this full diagonal line. Now there's a couple different things and some shadings. We'll get to that here in a second. A couple of ways you can graph that. You can, solve for one of your variables and then get it in slope-intercept form. I use the whole idea of, x and y intercepts and figured out, the different endpoints right here. Now think if you go and find your intercepts, and you can find them by like plugging in 0 for A, solve for E, and then plug in 0 for E, solve for A to figure out how many acoustic and electric guitars. If you go and do that, you should get over here 0, fiddle right here, 0, 16 for your electric guitars. And then I think your acoustic guitars down here, you would have, I got written down here, 48, 0. So just take my word for that, for that one right there. Now the other big things here, so we talked about that line right there. The other constraints here, we said we can only make 36 acoustic guitars. So we have to cut it off right at 36. So we draw a vertical line there going up and down. That's where we're going to cut off. So this over here, we kind of disregard that piece right there. And then the same thing with the electric guitars. Electric guitars, you need to, you can only make at least 10 of them right there. So we do a horizontal line here with the electric guitars right there. And this part, I guess, highlighted here in purple right here, this is the feasible region right here. Those are all the different combinations of guitars that we can make here. We can make 0 guitars of each. You can make at most 36 acoustic guitars. You can make at most 10 guitars for electric. Now, as far as these points right here, you need to find those vertices. So we know that the first number should be 36, comma, and we don't know what goes in that blank here. So we find whatever goes in that blank by plugging that back into this equation based off of the hours there. So if you go plug in 36 for A and then go do the math here, I already have it written out, you will get 4. So you can take my word for it, you can work it out. I'm just trying to keep the video kind of short. Now same idea for this other vertex right here. To find that other vertex, you're going to plug in this case here, we know that the electric guitars has to be 10. That's the maximum we can go there. And then if you go plug that back into the same equation, apparently you're going to get 18. So you got these different combinations. You can go 18, I guess, acoustic guitars and 10 electric guitars, or you can go 36 acoustic guitars and then 4 electric guitars right there. All right. So the whole idea with linear programming is one of these vertices right here of my feasible region is going to be the maximum, and then one of those vertices, if I plug in both, the A and the E, if I plug it in, one of them will give us the minimum profit right here. Now the minimum profit, you could probably guess, is 0, 0. If you plug that back into your profit equation, that will be a small profit right there. If you go and look at, for example, like 0, 10 versus 18, 10, obviously if you do 0 acoustic guitars and then 10 electric guitars versus 18 electric guitar or acoustic guitars and then 10 electric, obviously you're going to get more profit from this one right here. So definitely need to look at that point. Same thing with this 36, 4. The 36, 0, that's not going to be a bigger number when we plug it in. But as far as like which one is a better combination, we're not exactly for sure. So we're going to take both of these points right here and then we're going to plug them into the profit equation right over here. So both of them. Okay, so we'll work one out, and then we'll get our answer, and then we'll work the other one out here. So if you do that, let's go 1810 first. So let's see what kind of profit we get there. 45 times 18, and then plus 120 times 10. And that was based off of your profit equation. You know, this one I actually wrote out for you guys, but you can probably see where it comes from here. It's 45 per acoustic guitar and then 120 per electric guitar. So if you plug all that in, you're going to get, I have the final thing written out here. That's going to be $2,000.64 or $2,064 right there. Okay, and that was with the 18, 10. Okay, so I guess I'll color code it here. I'll do the second vertice right here, the feasible region, in green. So this profit here, you still go 45, but you're going 45 times 36 this time, and then plus 120 per the 4, I guess, electric guitars. And when you punch that out, that gets you $2,100 right there. Okay, so as far as maximizing profit, which combination maximizes your profit, you want to go 36 acoustic guitars. No, it's not one on the right here, I'm sorry. So 36 acoustic, and then apparently 4 electric. And that will maximize your profit. And that's a real world application of linear programming.